Neil and I's semester-long research project, the topic of which was the neutralization of Lossy-Compression induced image artifacts using convolutional neural networks. So the basis and motivation for this research is the fact that most images we find on the internet today undergo compression at some point. And the most common compression algorithms often result in the loss of certain details, like edges, corners, and textures, which make computer vision tasks like feature identification considerably more difficult. So the approach we took, implement a convolutional neural network to neutralize these anomalies and restore arbitrary images. Our project is built on top of the Python language. Several libraries came in handy. NumPy and SciPy were of great importance for easy data processing. The base of our machine learning was built on Google's TensorFlow library, and the deep learning was implemented with the Keras library stacked on top of TensorFlow. The proof of concept data was sampled from the MNIST handwritten digit database. And after the proof of concept working, we used the validation data from ImageNet's large scale visual recognition challenge from 2015 to train our model. From these 20,500 images, we randomly sampled for training data 300,000 32 by 32 grayscale patches, 5,000 of these for validation and 30,000 of them for test. We created their JPEG compressed counterparts with a batch compression script for the input to the network. Our network utilizes a 9-layer architecture. There's 5 convolutional layers, 2 max pooling, and 2 upsampling layers arranged as you can see here. So to actually implement the learning, we used the Atom optimizer for stochastic gradient-based optimization. Ultimately, we ended up training for about 400 epochs using an NVIDIA 980 Ti GPU.
So after many hours of training, you can see that we got pretty good results. These are just some examples of 32 by 32 patches. And you can see that the blocking artifacts are heavily reduced. There is some slight blur going on to lose some fine details, but for the most part, especially in images with straight lines, you can see that a lot of the edge is maintained. So while the model was trained on 32 by 32 image patches, it's fairly simple to run a full-sized image through the model as well. And so you can see here an example of a full-sized image of an office. There's a lot of compression artifacts you can see, especially along certain edges. And here's our restoration, which cleans up a lot of the compression artifacts. Although compared to the original, there is some fine detail loss, although the most jarring compression artifacts are removed. And here's just another example of a more heavily compressed image. You can see there's a lot of heavy compression along the contrasted areas of the lake. And with our algorithm, we can easily remove a lot of the high-frequency compression. And one important thing to note is while we do lose some fine details compared to the original image, the network does do a fairly good job in determining what details are important to keep, such as for the wooden floor there. Also keep in mind that these images are blown up for the presentation. They are originally of size 256 by 256, so the blurriness is definitely more pronounced in these scaled up images. A little side experiment we wanted to run was to see if we could run each of the red, blue, and green channels of a normal color image through the network and see how well it would perform. Since the network is only trained on grayscale images for reducing the dimensionality of the input data, it does do a fairly good job at removing noise. However, you can see that the color artifacts are actually ignored, and you can see some blockiness where the original colors that were artifacted used to be. And so it would be an interesting extension of the project to train the network on colored images with the additional 3 dimensions of data and see how well it would perform on the same exact image. For further extensions of the project, we could use colored images as training data, as I said before. We could also train on a wider variety of images. One thing we noticed was that with the computer-synthesized images that were much cleaner in general than real-life photos, the network performed kind of poorly. And lastly, if we had more computational resources and longer training time, we could possibly train on larger patches or even possibly the whole image in order to retrieve some sort of semantic information in the image that might assist in restoring the image. In general, this was a fairly ambitious project, especially considering neither of us have either worked with convolutional neural networks or neural networks in general. But I think we got pretty good results. And I want to thank you for watching. I hope you found it interesting. And all of our source code is openly available on GitHub. Thank you.